Okay, so force of gravity, right? So we say force of gravity. Now, what is a force of gravity? It's your weight, right? So your weight is the force of gravity. It's like how much gravity is pulling on you. That's the force of gravity. So how you test yourself? Well, you get on a scale, right? You have to put the scale on the ground, and then you step on it, and then you weigh yourself. And that's how. Now, what if you're in the air, like you're jumping off an airplane? Then you're weightless. You have to be on the ground, or you can be on the airplane, someplace solid that you actually, the force of gravity is acting upon you. So then you step on it and you weigh yourself. So that's the force of gravity. Now, if you're an airplane, because you're farther from the earth, you're going to weigh just a tiny bit less, not much. But that's the question we're going to have right now. How much would you weigh if you move away from the earth? And then we'll get into the space station and we'll check the astronauts' weightlessness and we see why are they weightless. They're not that far away from the earth. Does anybody know how far away the space station is from the earth? It's like a couple hundred miles, but it gets closer to the earth. It gets a little farther from the earth, so it's not exactly as, a circular orbit. It's elliptical orbit, just like everything else is elliptical orbit, right? All right, so the force of gravity, which is your weight, this is weight, is equal to that thing we call G, which is gravitational constant. Gravitational constant. And this gravitational constant, they measure it with really weird apparatus. It's like the first time they've actually measured this gravitational constant, which they're trying to do is to find out how does mass in this universe really work? Like, what is the atoms in this universe? What is the mass of an atom, basically, in this universe? And only in this universe. So the way they do it is really weird. Like what they do, they put, just quickly, you don't have to know this, but I want to show you why. So what they do, they have little tiny balls here, and they put this on the earth. They put this big, massive ball on the earth, and then they hang these guys here. There's little balls here. They hang them on a little string, really, really thin string. And then they put a little piece of wood top of here. And then this piece of wood is also hanging on a little thing here, like that. Now, what they do, they have to watch this little line here. This little line here is going to move because these little weights, they're attracted with a big weight. So not only this guy here is attracted to gravity, like the gravity is going to be pulling it down, it's also attracted to this ball here, right? And remember, now this is a mutual thing. So the ball attracts the little ball attracts the big ball, the moon attracts the earth attracts the moon. And so if we take a look here, this ball is going to move a little bit. So when this ball moves towards the big ball, this big apparatus up here is going to start twisting. Now, if you're in the room, you can't measure it because your weight also comes into effect. So somebody goes outside someplace with a telescope, watch to see how much this thing here moves. This little wire moves. And because it's hanging here, it's kind of spins like this a little bit, like that. And approximately, when they did it the first time, it was 4 millimeters, right? 4 millimeters is, it's about that much, right? 4 millimeters. So it moves just a tiny, tiny bit. And that told them what that G was. So G, at the moment, we don't have to worry about it. I just want you to know what it is and how they measure it. Otherwise, you don't need to know what it is exactly. Now, we also multiply this times mass of one object times the mass of the second object. So these objects here, they're attracting each other, right? So as they attract each other, they have a distance between them. In this case here, like the distance between the tiny ball and the big ball, that's distance to the power of 2. distance to the power of 2. And okay, so this is the formula. What it's telling me is the more mass the objects have, the greater your weight. So if you have more mass, if you have more stuff in your body, you weigh more. That's all. It's simple. Now, it also tells me that if you move away from the earth, like if I go on top of a mountain, if I go on an airplane way up in the air someplace and I weigh myself, I would have less weight. That's what it's telling me. So now we're going to want to figure out, well, how much less weight? And why is it that the astronauts are weightless if they're only 200 miles above the surface of the Earth? So that's what we're going to do now. I'm going to simplify this equation, write it another way so we can all see it. Let me kill this. All right, so here is the Earth. Here's the Earth. Here is the center of the Earth. Mass number 1 here is going to be the mass of the Earth. So this is mass 1, or M1. And then we'll put somebody on the surface of the Earth. Let's call this Sina. So this is Sina. Now, my mass is going to be mass 2. Doesn't really matter. That could be mass 1. The Earth could be mass 2. So I have some mass. The Earth has some mass. Now, the Earth is attracting me, right? But remember, I'm also attracting the Earth. So the Earth is attracted by me as well as me by the Earth, right? It's a mutual thing. Now, I have a distance between the center of the Earth and me, and that happens to be distance d. D, right? So, okay, so this is M1, this would be M2. And so I'm going to go on top of the Earth here. I'm standing now. I'm going to weigh myself and go, I weigh 200 pounds. Well, let's just assume I'm only 160 pounds. Well, let's just say I weigh 200 pounds. So this guy here weighs 200 pounds. What happens if he moves away from the Earth? How much would his weight go down so we can figure out, does he weigh 100 pounds, 200 pounds? Let's see. I'm going to move, well, actually, I'm going to rewrite this equation to make it a little simpler. I write down force of gravity. Force of gravity is equal to G again. Not to worry. Then times mass 1 times mass 2 divided by distance d to the power of 2. Right? So let's move away. So this is just 1d here. That's about 4,000 miles in the case of the Earth. It's the radius of the Earth. So the whole Earth is like 8,200 miles in diameter, right? So we say 4,000 miles is about what this d is. So this is d. This is d from the center of the Earth to the surface of the Earth. And then we'll move away another d. So this is another d. So this is 2d now. This is 2d. And let me put myself here now. I'm over here. Okay, what's my weight now? Let's take a look. So we say force of gravity is equal to G times M1 times M2 divided by, now distance here is increased. Now it's twice the distance. So we're going to put down 2d to the power of 2. So we're going to put down 2d to the power of 2. 2d means, 2d squared means 2d times 2d. So what is 2d times 2d? Well, let's see, 2d times 2d would be 4d squared. So this would be, I forgot the g. 4d squared, like that. Okay, now this is going to be smaller weight, right? Because we're dividing this whole thing by 4, so it's going to be dropping 4 times. Now, I'm going to bring this 4 out. So instead of saying this, I could say 1/4 of G times 1/4 of M1, M2 divided by D squared, like that. So these two things are exactly the same. This is exactly the same as this, right? Now, what is the difference between this and this?
You forgot the G again, I think.
I did. Yeah. Here. Okay. So what is the difference? 1/4. So your weight is going to be 1/4 as much now if you move twice as far away. So every time you move away from the Earth, the distance has to be multiplied times itself. So 2D squared. All right. So now we have 4D, so it'd be 1/4 as much. Now, if I had 200 pounds, it'd be 1/4 as much, or my force of gravity, which is my weight, is going to be equal to 200 divided by 4. Because we said force of gravity is weight, so all of this is weight, right? This is all weight. That's all we did. So we took all of this out. This is 1/4 of my weight now. So it's 1/4 of my weight. This would be 50 pounds. So I weigh 50 pounds. If I go 4,000 miles away from the center of the Earth, I'm sorry, 8,000 miles away from the center of the Earth, it'd be twice as far. So if I go twice as far away from the center of the Earth, then I will weigh 50 pounds. All right, but I got to go 4,000 miles away, right? So let me give you one more example. This time, we're going to go 10 times away and see what happens. So I'm going to remake this whole thing again. I'm going to go 10 times the distance away now. All right. So let's see. So here's the Earth again. Here's the center of the Earth. D is going to be this. That's D. Now I'm going to go 10 times farther. So I'm going to go one more D, another D, another D, another D, another D, another D, another D. 1, 2, 3, 4, 5, 6, 7, 9. All right. So now I'm going to be 10 times D.
Always going to be square rooted to 2, right, Professor?
All right. Square root?
Like, you know how the 2, like on the formula, it stays 2 for everything. So it'd still be 10D to square root of 2. Or like 2 to the power of 2, I mean.
No, instead of 2D, it will be 10D now, right? So when we write this formula now, it's going to be force of gravity is equal to G again. M1 doesn't change. M2, my mass and the mass of the Earth haven't changed, right? That hasn't changed. So the only thing that has changed then is this. We have 10D to the power of 2, like that. You see? It's 10 times the distance. It's not just distance now. This is the original formula. We just have 10 times the bigger distance, that's all. Do you follow? I'm not hearing from you.
Yes, Professor.
Okay, great. All right. So now, this would be force of gravity is going to be equal to G times M1 times M2 divided by 100 D squared. All right. Now I can rewrite this again to make it easier to see. It'd be 1/100th of G times M1 times M2 divided by d squared. So it's exactly the same thing. This?
Would it be 2 pounds?
Correct. It will be 2 pounds. So this is exactly the same as this. The only difference is this 100th. So my weight is going to go down 100 times. So if I weigh 200 pounds, now the force of gravity, my weight is going to be 200 divided by 100, or 2 pounds. You'd be correct. So I'll weigh 2 pounds, but I got to go pretty far away. I got to go 40,000 miles away before my weight drops to 2 pounds. Still not weightless, still weigh 2 pounds. All right. Although I don't know how you're going to weigh yourself because you have to have a scale and everything, right, to weigh yourself. All right. So if I give you a question then, I'll say like if you moved 5 times farther from the Earth, how much would your weight go down? You say 5 times 5, 25 times less weight. If I tell you you go 6 times farther, you're okay, it'll be 36 times less weight, like that, all right? So
I have a question.
Yeah.
With this formula, it looks like no matter how far away you are from Earth, it'll always have some kind of influence on your weight.
Very good.
So
That's
is there
a
a point where it stops?
That's a very good observation, son. What is your name?
Trevor Shaw?
Trevor, that was an excellent observation. So here's the deal. If I have mass, this thing has mass, right? So the mass of this thing here can be noticed by God himself on the other side of the universe, right? So gravity never goes anywhere. It just continuously travels. It'd be imperceptible unless you've God and you can measure the weight, right, or mass, but its gravitational effect is forever, infinity. You're right, absolutely correct.
Thank you.
You're welcome. All right. So if the moon's distance from the Earth is doubled, how much would the influence go down?
Would it be 1/2?
No.
1/4.
Sina, go ahead.
1/4.
1/4, or 4 times, yeah. So if you go twice as far, it'd be 4 times. If you go 3 times farther, it'd be 9 times. If you go 6 times farther, it'd be 36 times less. If you go 8 times, it'd be 64 times less, like that. So if I said twice, so if the moon's distance is doubled, its effect on the moon, the effect of the Earth on the moon and the moon on the Earth, will be 4 times less, right? Okay, so like the tides on the oceans are going to be a lot less, right? They're not going to be huge tides. All right, let me erase this now. All of this work for just one question? Sheesh. But it just goes directly into the next question. Why is it that the astronauts are weightless then? If all of this is true, why are the astronauts weightless? So let's see. Do you guys know why Sir Isaac Newton developed calculus? Does anybody know? Why did he invent calculus? He invented calculus so that he could calculate stuff in the future. Like what happens if something is moving? Then he broke down all those motions into little tiny, tiny motions. And then there's something called integral. He integrates over this huge motion of the objects. He can figure out exactly how the object is moving. That's why he developed calculus. I'll show you how. You can break down this giant motion into little tiny motions, right? That's the derivative of something. Well, that's okay. If you don't understand it, it's fine. No worries. Let's draw the Earth. And on this Earth, I'm going to put in some guy here. So here's some guy. Maybe it's me. I have a gun. And it's an AK-47. And I'm going to shoot a bullet, all right? What happens if I shoot a bullet? Well, the bullet is going to go kind of like this. It's going to hit the earth. Far away, but it's still going to hit the earth, right? Why does it do that? Shouldn't it just go on forever and ever? Shouldn't this bullet go forever and ever and ever and ever, right? You can't change the velocity. That's inertia, the law of inertia. So why does it go down then?
Because of the gravity and the.
That's one of them, right? Because of the gravity. It's an external force, so its velocity is going to change. That's very good. That's correct. But also, there is somebody say something?
Yeah, it doesn't go fast enough.
Right, but why does it go down?
It gets friction.
Because
Friction, very good. Friction. I was trying to get to friction. You're right. Friction. So yeah, there's friction too. Like if I drop this pen right now, it'll fall, right? Everything falls towards the earth if you let it go here. And it accelerates towards the earth at 32 feet per second. And then it accelerates at 32 feet per second. So it'll be 32 feet per second per second. So in the second, if I drop this, the first second is going to go at 32 feet, accelerate towards the earth. Then it accelerates another 32 feet. So after 2 seconds, it'll be 64 feet, right? The 3 seconds will be 96 feet. It just accelerates, right? And so by the time it drops, it's going to go pretty fast. That's something called, we call it G, like you say, I'm going on an airplane and I'm speeding up, accelerating at G. That just means the same thing as this G. This is the gravitational influence of the Earth. It accelerates the objects. That's called G, the acceleration in the Earth's gravitational system is called G, right? This just falls like that. That's a small G, not a capital G like a gravitational constant. All right, so now, if I don't want the air resistance, I'll go into space. So if I go to space and I shoot my bullet, it'll go on forever and ever. Unless there's an external force, like maybe the earth or something. So I got to shoot it fast enough, like, I think it was, who said that? Was it Mr. Farmer said that? Somebody said that.
I did.
Yeah, okay. So now if I shoot it fast enough, and there's no air here, right, for friction, lack of friction, this bullet can go around the earth if I shoot it fast enough. At some point, it'll get into orbit. But it has to be just the right amount of force, right? So I got to send this guy out, and this thing will go around the earth. Remember, if there's a lack of air resistance, if there's air resistance, it's not going to happen. So we got to go outside the earth and shoot a bullet to put it in orbit around the earth like this so it can continuously follow this motion. All right. Now, I'm going to put the astronauts here now. The astronauts are only 200 miles above the surface of the earth. So here is the astronauts orbiting the earth, and I'm going to put them in the space station. So make us some space station here. Here's the center of the earth. Here's our space station. There's the space station. Now, you can see there's a motion of the space station, right? It goes around the earth like that. Well, what Mr. Newton is telling us is you break it down, right? You go break it down like this. You go, all right, you draw a line from the center of the earth to the position of the space station. And you go, all right, so we got two motions here. One motion is the object is going like this. And another motion is the object is falling towards the earth. So it's going this way and falling towards the earth continuously. So it goes that way, it falls towards the earth. Goes this way, it falls towards the earth. Goes this way, it falls towards the earth. That's where calculus comes from. So these little tiny motions, if you add them all up, it'll make up the circle for you. Right? So that every one of these will be a derivative of the motion, right? It'll be a little tiny, tiny motion. So we can break it all down and go, okay, so all these motions are all going away. So if I draw a line here, its motion is going to be this way, perpendicular here, and then fall towards the earth. This way, fall towards the earth. Now, if you're falling towards the earth, you're weightless. You don't have any weight at all. You're just falling towards the earth. But if you want to weigh yourself, you have to be on the surface of the earth or in an airplane or something where you can put a stable way to measure yourself, and you get on the scale and you weigh yourself. But if you're floating, if you jump off the chair, jump off the table, jump off a building, you're weightless. Even though you're weightless, you're still not massless, so you're still going to fall towards the gravitational force, but you're weightless. So your weight only counts if you are on the earth itself, if you can measure yourself on the scale. So these guys here, because they're falling towards the earth, they're going to be weightless, even though they're only 200 miles away. And from our formula, 200 miles is nothing. Remember, we talked about force of gravity is equal to G times M1 times M2 divided by D squared. So the D changes maybe, 200 miles. This is 4,000. D from the center of the earth to here is 4,000. They're only 200 miles above the surface of the earth. So if you could have a stable place to weigh yourself, you weigh about the same. If you're 200 pounds, you weigh 200 pounds. But if you're falling, you're weightless. You can do somersaults and stuff. If you jump out of an airplane, before you open up your parachute, you're weightless. You can do somersaults. If you go to Disneyland, the Tower of Terror, you're weightless. If you put this pen, let me get a different color pen though. Let's say I put my pen on my knee here, and I'm falling on Tower of Terror, then this pen is going to float above my knee like this. It's going to be weightless because you're free falling. So at the Tower of Terror, and it's going to open up in April, so you guys can still go. If you go to the Tower of Terror, you're free falling. They let you fall. The force of gravity go like that. As you fall, you're weightless. All right. Okay, so now what happens if I go on an airplane? They take me up like this, and then the airplane drops. Will you be weightless inside the airplane? The answer is yes. You'll be weightless. Everybody in the airplane will be weightless. So that's how NASA trains their astronauts. They go up like this, and as they drop, weightless for maybe 30 seconds, and then up again. The entire movie, Apollo 13, was made this way. But Tom Hanks was weightless. The first few times, they made the airplane really filthy because they were, getting sick and puking and everything. That's why they call these flights what did they call the puke comet? Something like that, right? So I was going to show you that. I want to show you what happens if you get into the airplane, go up, and then come down. What happens inside that airplane? You can feel weightlessness.
What it's like to be weightless. I was really freaking nervous about it because a lot of people do throw up. And if you throw up, you have to get back in your seat for the rest of the flight. So basically, it'd be the most expensive vomit of your life, unless you threw up into somebody's Gucci bag. For each parabola, you get about 30 seconds of weightlessness. And we did 15 of them. So I got about 7.5 minutes of glorious weightlessness. So without further ado, here's some footage of me having the freaking time of my life. So I was supposed to narrate this as it went, but I could get no intelligent commentary out of myself. I have no idea what this is. Yeah, that's about it. As the airplane is going up, you're laying down on your back, and first you're getting heavier and heavier and heavier, but then you're getting lighter and lighter and lighter until you just float out. It was really like flying, and your body doesn't really know what to do. Your instinct is to just pedal, which is terribly ineffective. Oh my God. They threw out some water and got to catch some candy. I feel like fucking Pac-Man.
Okay. It looks like fun to me, you guys. I would do it. I'd definitely go up. All right, so is there any questions before I segue to differential gravitational force?
What did the Epsom salt have to do with it?
It made you weightless. She was trying to see if she can stay weightless without puking. That was practice for her. Do you follow? So she was moving around in weightlessness, basically, right? You feel weightless if you go inside that salt water. You float.
Oh,
Yeah. So she was practicing so that she can go up there without puking. You know, like when they did it, the movie Apollo 13, the first few times when they throw up, the stuff is everywhere. It's floating too, right? So you can't not run into it. You don't have a choice. Like you can't do this and move around. There's no movement. If somebody pushes you, then you move. Otherwise, you're helpless, right? Whatever direction you're going, you continue to go in that direction. Unless some external force, like somebody grabs you, pulls you, pushes you, you can't change directions. I just wish that she wouldn't use the bad words all the time, but it was kind of a cute movie, I thought. All right, last thing, because we're going to be talking about black holes later, I want to make sure you guys follow what I'm going to be telling you next, which is about how the Earth has tides, right? Where do the tides come from, right? So it's an explanation of tides, basically, so you guys can see why there's tides on Earth. What causes the tides on Earth? All right, so let's take a look now. We already made this guy go into orbit. Okay, so here's the Earth. Here's the Earth. Here's the moon. So there's the moon. There's the Earth. And so the gravitational force upon the Earth and gravity of the Earth upon the moon is a mutual thing, remember? And we said the center of gravitational force is over here. So in this case, the moon orbits this point here. So it goes around this point, not the Earth center, this point here. So the moon goes like that around the Earth. Now the Earth itself also goes around this point. So the Earth does, so it's a mutual thing, right? The Earth does this, the moon goes around the center of gravity. However, let's take a look to see how does this gravitational force affect the Earth, right? So we said here's the center of the Earth. The gravitational force of the moon is pulling on the Earth, right? Like that. However, if you look at this side of the Earth, it's closer to the moon than the center of the Earth. So here's the center of the Earth. And this is a far side of the Earth, right? Okay, so which one is attracted the most? The side that faces the moon, the side that is farthest from the moon, or the center of the Earth? Well, the answer is the side that is closest to the moon. So let's put some arrows here. These arrows mean how much you're attracted to the gravitational influence of the moon. I go, this side is a lot. So now the Earth's, instead of being here, let's move it over here. We're exaggerating so we can see what's going on, all right? This is just an exaggeration. So this side of the Earth, instead of being here, is moved over here. The center of the Earth is also going to move. So the center of the Earth is moved this much. So instead of being here, the center of the moon, the Earth is over here. This is like the new center of the Earth. This is the new side of the Earth. And then what about this side? Well, this side is going to move too, but not as much as the center of the Earth, and not as much as the side that faces it. Again, I'm exaggerating. So this side is moved this much, just a little bit, all right? So those arrows are just basically telling us the side that is closest to the moon is being pulled the most. The center of the Earth is pulled, but not as much as this side. This side is also pulled, but not as much as the center of the Earth or this side of the Earth. So now we have this as the new side of the Earth, this as the center of the Earth, and this as the side of the Earth that is pulled. So the shape of the Earth is now changed to this, like that. All right, that's the new Earth. So now what happens is two sides of the Earth. I didn't do this very good, actually. Do this a little bit flatter. Like this. So the Earth now looks like this. The water here, on this side, water has come up. This side, the water is kind of like left behind. So you have a water is coming up on two sides of the Earth like that. So one side of the Earth, the water is, imagine, pulled twice towards the moon. One side seems like the water is left behind. The center of the Earth has moved, but the water is kind of like left behind. It's not as been pulled as much as this side. So now the shape of the Earth is continuously changed. And as the Earth rotates, the whole Earth is going to go under the tides. So as the Earth is moving, it's rotating. Let's say this side here, the water is up. This side here, the water is up. And the Earth is moving under the water. So the tides are over here. The water is high on this side and on this side. This side because it's closer to the moon. This side is because it's left behind. Now this side here, you have the low water. So you have the low tides. Here and here you have low tides. So you have low tides here. There's low tides here and low tides here. Because the water has to go from someplace. The ocean waters gravitate towards this side of the Earth and this side of the Earth because this one is left behind. This side is closer. So two bumps here. One bump here, one bump here. And this side here is lower water because the water has moved from here to over here. And the whole Earth is rotating under it. So everything works this way. If you have, let's say, if it's an astronaut close to a black hole, it's a big head. All right, so this astronaut is close to a black hole. Let's say this is a black hole now. Let's make this the black hole. Black holes actually have lots of mass, like a billion times the mass of the Earth, let's say, all right? But the size is 0, so you can get really close to it. You can get as close as you want to it. Size 0, there's no size to it, but it's got a lot of mass. So gravity is going to pull you. But just like the tides on Earth, here are your shoes. Your shoes is going to be pulled towards the black hole. This is a black hole. The most. The most. So it's pulled the most. This side here, your head is farther out. So it's pulled the least. And just like the Earth, your shape is going to change. Except this time, it's going to stretch you. So your toes are going to be pulled really hard. Your head is going to be, compared to your toes, is going to be left behind. So what's going to happen to you is going to make you into a spaghetti. It's going to stretch you from head to toe. It's the difference between the gravity on your feet and the gravity in your head. That difference is going to make you into a spaghetti. There's an actual word for this. This is called spaghettification. Spaghettification. So spaghettification is just the difference between one side of the object and the other side of the object as far as gravity is concerned. So if the Earth was closer to this, the Earth will also be spaghetti. This side of the Earth will be pulled the most. This side of the Earth is farthest out and be pulled the least. So the Earth is going to be stretched out and look like a spaghetti too. In fact, there's enough mass to make the whole Earth into a spaghetti. So we're going to have this giant spaghetti. Now, if an astronaut is falling in, this spaghetti is going to be as thick as atoms, right? It's as thick as an atom. So it's the thinnest spaghetti you can possibly make in the entire universe. It's an atom spaghetti, right? Any questions about that? All right. Right on, you guys. We'll talk about later about the black holes. When we do, we'll go over the spaghettification again. All right, let me get in here.
Question.
Yeah, please.
So just I've heard, I don't remember, I remember hearing about something about that, about black holes and stuff like that. And if that were to happen, theoretically, like it's too quick to happen to my knowledge. And I feel like since the feet are gonna get in first, like we wouldn't really like comprehend it because it's happening so quick. Is that right?
Well, I mean, we're talking about spaghetti. You're going to turn into a spaghetti. So you don't have a brain anymore. You're not going to see anything. You don't have eyes. You don't have a brain. You're not going to feel anything except being destroyed.
Okay.
You feel like your whole body is being pulled like this because of the difference between the gravitational force on your head and the gravitational force of your feet. If you get close enough, you're done. You're spaghetti.